Hello, Science 10, and welcome to our video on work calculations. You have already started in on lesson 4 in our last video, so we're just going to be working off of the next section called work. And today we're going to focus in on learning how to do the calculations for work. So in this lesson, you will learn what is the definition of work, how the formula is laid out, what are the units for each part of the formula for work, and then how to solve the equations using the work formula and rearranging it. You will need a calculator for this, so please make sure you have one. So let's start with kind of thinking about which one of these pictures shows the person doing work and why. So here we have a woman pushing a baby carriage, and here we have someone pushing on a brick wall. So I want you to think about which one do you think is doing work and which one is maybe not, or are they both doing work? And keep this in your mind, and we're going to come back to it in a second. So work is done when a force is applied to an object that moves in the same direction, so along the same line. So it has to be parallel of that force. So work is done when a force is applied to move something along the same plane as it. The unit for work is joules. It's a special unit that we're going to talk about, and it is known as a Newton meter. So when you see the word joule, it's actually two units that come together, the Newton and the meter, to make that a joule, which makes sense when we talk about work, and you'll see what to come together to make the joule in the work formula. So writing down what work is, a force applied to an object moving along the same direction. Let's go back to my example on the first page. Here I have a woman pushing a baby carriage and a man pushing on a brick wall. Okay. Both of them are pushing along the same line. The lady has the baby carriage in front of her and she's walking in the same direction. The man is pushing on the wall and he's pushing it in the same direction he is moving. It's parallel. But with our definition, it says that it has to move a distance in order for work to occur. So the woman is walking with the baby carriage. She might move 100 meters. But that brick wall is not moving 100 meters. It's not moving at all. So technically, the man pushing on the brick wall is not doing any work, even though it looks like he is and he's trying really hard. By the definition of work, that picture shows no work is being done because the wall is not moving. All right. So again, work is done when a force is applied and the object moves in the direction of that force. That wall was not moving, so no work was done. So let's look at the formula for work. So work is equal to force times and then delta D. Delta is the little triangle, meaning a change in distance. So we're moving a certain amount of the distance. Okay, so change in position. So work is always calculated in joules. Joules is always a capital J. F represents force, and it is always in newtons, which is a large N. And the delta D, which is change in position or distance, is in meters. So again, earlier I said that the unit for work is joules, and it's always because a joule is a Newton meter. Well, force times distance is newtons times meters, so it makes joules. So it makes sense that work is in joules because it's a Newton meter. The amount of work done on an object is determined by multiplying the distance that it's moved by the force that it took to move that object. So for example, if we were to look at an everyday example of the wind, okay, how much work is the wind doing against a tree and how much force is being exerted? Okay, so the tree is moving a distance in the same direction, it's bending over. How much force does it take will tell us how hard the wind is working. But again, you have to remember that distance needs to be in a parallel line. So it can be distance moving forward or distance moving backward, but it has to be in the same line that the force is applied. So if the wind is blowing this way, it makes sense that this is a distance because it's moving in one direction. If the wind was pushing up like this, but this was moving this way, that's not going to work. That's not in the same parallel line. Okay. And we'll talk about that when we more talk about vectors and scalars. So the force and the distance have to be parallel to each other. okay? And your variables have to be in the correct units, okay? So sometimes distance can be represented in centimeters, kilometers, it can be in decameters, it can be in a variety of different things, okay? You have to make sure that when you are doing questions that they are always in meters. Then you can plug it into the variable because work is a Newton meter. It's not a Newton kilometer. It's not a Newton centimeter. It's a Newton meter. So you have to make sure you always convert your distances to the right unit. So let's do a couple examples together, and then this way you have them in your notes for when you try and do your assignments. So example 1 is using the idea that an engine applies 1,000 newtons or 1,000 newtons is force to a car moving at 50 meters. So there's our distance. We're looking for how much work is done in a car. Every time you do an equation like this or something like this, the first step is to always list your variables. This will help you get comfortable looking for which variable am I looking for and do I need to rearrange my formula. So I have 1,000 newtons, which represents force. I have 50 meters, which represents my change in position. I'm looking for work. So now I can say, okay, well, this is easy because I can use just my regular formula. Work equals force times distance. I'm going to have to remember that when I do these kinds of calculations, I have to remember significant digits. So because I am multiplying, the rule for significant digits is that we use the smallest number. So 50 meters only has 2 significant digits in it. So my answer has to be to 2 significant digits. All right. So reminding yourself of your significant digit rules when you're doing calculations. So now I'm going to take all of my stuff and plug it into my equation. My newtons make sense. I have meters. I don't need to convert it. So I'm going to plug it in as is. So 1,000 newtons times 50 meters gives me 50,000 joules. There's my answer. Stop, because it's not correct yet, because we need to put it in significant digits. So you need to go and you need to make it so that there's only 2 significant digits. This is a problem though, because this is a really big number and there's more than 2 significant digits here because we have 50,000 joules. So we're going to have to use scientific notation to make this work. So what you're going to do is reminding yourself that the decimal is here. You're going to have to count till you have a number between 1 and 10. So I'm going to move my decimal 1, 2, 3, 4 spaces so that I have 5.0, which is 2 significant digits. So my answer ends up being 5.0 times 10 to the 4 joules because I moved my decimal 4 places to the left. It's a really big number, so I give it a positive exponent of 4. And that, ladies and gentlemen, is the correct answer for this question, using significant digits, scientific notation, and plugging my formula in. All right. Take time to write it all out. And there's not a ton of space there, and I apologize, but please try to fit it all in. And then let's move on to the next one. So example number 2 is all about pushing on a wall, which might sound familiar because I've already kind of talked about this. So you push on a wall with all of your strength, all 500 newtons of it, but the wall doesn't move. How much work was done on the wall? Well, let's talk about this. We have work equals force times distance. If I look at all my variables, I have force at 500 newtons. I have distance at 0 meters. So I'm solving for work. How much work? So I'm going to plug my stuff into my formula, 500 newtons times 0 meters. All right. What do I get? 0 joules. Nothing was done. There is no work done. You cannot push on a wall and do work because the wall does not move. Okay. So please remind yourself that if you are talking about a distance and something doesn't move, no work is going to be completed. In the next 2 examples, we're going to learn how to rearrange this formula because this is going to happen to you and you're going to have to know what to do if you're asked to solve for distance or if you're asked to solve for force. So in this case, you do 43 joules of work by applying a force of 5.21 newtons on a shopping cart. What is the distance that you are applying this force to? So again, put your variables down. Work is 43 joules. Force is 5.21, newtons, it should say. I forgot my units there. I'm solving for distance. So we need to rearrange this formula because the original formula is force times delta D. We need to isolate delta D to be all by itself. How do we do that? Well, we look at what is the operation in between. It's multiplication. Now you just do the opposite. So you say, okay, I need to divide force on this side to get rid of it. But what I do to one side, I always have to do to the other. So I'm going to divide work by force. And this is what I get. Delta D equals work divided by force. So now that I have my equation figured out, I can plug in my numbers. So 43 joules divided by 521 newtons is 224.03 meters. Not the correct answer yet. You're probably thinking, but that's what my calculator told me. But let's look back at what we're doing. We're dividing, and each of these has 3 significant digits. This does not have 3 significant digits. This has 5. So what you need to do is you need to put it into scientific notation. So let's put it into scientific notation using our 3 digits. Sorry, that's covering it. So again, moving the decimal place over to make a number between 1 and 10. 1, 2. I'm going to get 2.24 because I need to have 3 significant digits. I moved my decimal 2 places. So this ends up being 2.24 times 10 to the 2 meters. Again, using scientific notation to put a larger number into a way that we can read it and make sure that we have the correct amount of significant digits. All right. So that's how you rearrange the formula if you're looking for distance. We're going to try one out for trying out on force. Now, the cool thing is it's the same rearrangement because work equals force times distance. Force and distance are always going to be multiplied to each other. So when rearranging the formula, we just divide work by the other variable. So this is a car, takes 45 meters to stop, and the brakes do negative 4,800 joules of work. What is the force exerted by the brakes? So at the bottom, it says, in what direction is this force exerted? You'll notice that force is a negative number in this case because work can be done in the same direction, like force and distance can go in the same direction, or sometimes force can go in the opposite direction. As long as they're parallel to each other, it's okay. But if force is going in the opposite direction or work is going in the opposite direction, okay, you're going to have a negative number. So think of brakes. You're going along, you're driving, you apply brakes. It's putting a force trying to force your car, not backwards, but to stop. That's an opposite type of opposite force, so it's going to be negative. So here I have my 2 variables, work and delta D. I'm solving for force, so I need to rearrange my formula. Looking at my original formula, I'm going to do the same thing I did to the last one. I'm going to take delta D this time and divide it out. So divide by delta D on this side, because remember, multiplying, the opposite is dividing. So it cancels these out, but what I do to one side, I always do to the other. So work is going to be divided by delta D. So this is my new formula. Force is equal to work divided by D. I'm looking back at my equations. Back at my problem, and I'm looking to see how many significant digits I have. Now, in this case, I'm going to use 4 significant digits because I'm going to assume that 4,800 is an exact amount. It's 4800.0. Okay, we're going to just keep it simple for this. We could say 2 significant digits, but just to help us out to solve this question, we're just going to keep it at 4. So I'm going to plug in my numbers and I'm going to get an answer of 106.666 repeating. So I'm going to round it up to 106.7 because I need 4 significant digits. But the other thing I need to do is I need to add a negative sign because there was a negative here. A negative divided by a positive is going to be a negative. Okay? So when we talk about the way the force was applied, it was applied in the opposite direction of movement. All right? So these are the 4 examples. You are going to do a couple more examples and work through an assignment. Please let me know if you have any questions or concerns, and I will talk to you later.